So in this video, I'm just going to go over some of the common connections to a flight controller, such as the Cube. So some people may have seen this beautiful graphic here showing what you can sort of hook up to a Cube and where it goes. I'm just going to talk about that in a little bit more detail. So here we have the Orange Cube Plus, something that I use every day. And in just order to assist people getting started or unsure of what to connect where, I'm just going to go through each port on this and talk a bit about what you can connect to it and any sort of do's and don'ts and any little caveats that catch people out. So first of all, when you get any modern flight controller, you need to flash the firmware on it. So that's done by using your computer software, such as Mission Planner and the included USB cable. So that will power the device and allow you to flash the firmware, such as Ardu Plane, Ardu Copter, Ardu Rover to it. Now in normal use we must power the Cube, so the USB shouldn't be used to power it in flight. We have the option of two power connectors, power 1 and power 2, and they will provide the autopilot with just over 5 volts of power. So this is an example of the cable that is connected to the Cube here. This is a Molex ClickMate 2mm or 2.0. What you'll see here is we've got 2 red wires and 2 black. That is simply the power to the Cube, the 5 volts. And in the middle we have a current sensing and a voltage sensing wire. And this is what provides information about the battery connected to it. So within a Cube in the standard set, you get something we call the Power Brick Mini. So this has the same connector on it, the Molex ClickMate, with the 6 wires, so providing power, current and voltage. So what this power brick will do is, I like to look at this as an inline current sensor. It will tell you the voltage of the battery connected to it, and it will measure the current passing through it, and it provides that information to the autopilot that it can use to present you with voltage and current information. This piece that comes with the autopilot is rated up to 8S and to a continuous current of 30 amps. So quite often we get questions such as, oh, I need to use more current, or what if I use 12S or 24S? What do we do then? Well, there's a range of aftermarket current and voltage sensors in all different shapes and sizes to allow you to measure the voltage and current. Here's an example of one in a different layout. This is a Holybro PM06. Now we do some of these that will actually go up to 14S. We also have the MAUC system, which also goes over 12S and even up to 100 volt sensing. And there's many different solutions to allow for inline current sensing or also higher voltage sensing. The example here of this Holybro PM02, this is a very nice solution to connecting a quadcopter. So we have the same connection, this 6-pin plug here that could plug into power 2, and we also have pads which will allow us to solder on some ESCs, and this system here could provide the power to some auxiliary equipment, to your motors, and also provide a current and voltage measurement. We'll also see we have a power 2 socket on the Cube, so we could have redundant power supplies if that was your requirement. So if your primary power supply failed, you could have a secondary one here which would be used in that case. Let's have a look at the connections to the rear of the Cube. So I normally refer to this as a servo rail. It has 14 outputs, what we call 8 main outputs, and then these 6 auxiliary outputs, and we also have RC in. So a normal setup on here might be to connect your servos and motors for your aircraft or rover or multi-rotor. So these could be PWM outputs or D-shot outputs, which you would define in the software. One thing to note on this rail system here is the ground is common and the sort of middle pin positive is common, but it doesn't provide power to your devices. So if I was all up and running and connected a servo to it, let's just put this into main 1, and let's say for example I have my power to the Cube, the Cube would power up and light up and the code would be running, but the servo is never going to move in this scenario because it has no power provided to it. So what you would do there is you need to put a BEC or a voltage, some sort of voltage regulator onto the rail, or if you're using a ESC with a built-in BEC, to provide power to the rail. So here's an example of a very common, pretty good BEC that'll provide 5 volts at 4 amps. So what you'd have to do in order to get the servo to work would be to provide power to the rail and your servo connected. As long as your BEC's powered and you're set up and you've got your controller set up and enough settings done, this now is powering the servo and allowing it to function. You can use a bit higher voltage on this rail. You can go up to 10 volts, but what you should be cautious of, say, the size of servos you're plugging in and the current draw across this rail. It is just the sort of dew point pins. If you're providing a lot of servos, you may wish to connect the BEC in multiple locations to spread the current across the pins. If you're using extremely large servos, you may wish to power them outside of the cube, so not use power here, only connect the signal wires and provide power to the servos either on their own to the PDB, or there is a few products available, for example a Hobbywing 25 amp BEC that allows you to power your servos off the rail but still connect your signal pins. So there was one other connector on the rear here, and that one's labelled RC in. That's exactly what it is: receiver in, radio control in. 3 pins here. So our traditional receiver here, what we've got a RX8R that would connect in. Now this port will provide power, so this port will provide enough power for this receiver. It will not provide enough power to connect servos as well to receiver. That's a sort of very bad practice in a radio control system. So in the past we've seen people connect, for example, a landing gear servo into this receiver without additional power. That would be enough to sort of to crash the receiver, if you like. So yeah, this RC in port will provide sufficient power to power a standard receiver, but there should be nothing else connected and drawing power from this receiver. Some other types of receiver will connect in different places. So we have a dedicated Spectrum port, and also if you're using something with CRSF, they will connect to one of the serial ports, such as a telemetry or a GPS port. We'll come to those shortly. We have an additional socket here labelled S-Bus with an O at the end, so that's S-Bus out, not to be confused with putting S-Bus in, which is what you'd put on your RC in. So that allows you to actually retransmit, if you like, the S-Bus out. So if you've got a receiver connected here, you can resend it out. So some user cases could be connect to a gimbal or another device or something to log the S-Bus. So yeah, some users would use that. There is also a debug port here, an additional serial port next to that, but with these ADSB carrier boards, that's not available as standard. So the only one available on here is S-Bus out. These other pins here aren't used on the Plus. You may have noticed the antenna sticking out. So as standard, these come with an ADSB receiver, so receive only, not transmit, and that is essentially a ping RX from UAVonic that is built on the board, and that allows you to see other air users that are transmitting on ADSB. On the side, we earlier showed we will connect a USB in order to flash the firmware. Underneath that is the SD card. So an SD card is necessary on the flight controller, and it's where you would store your logs, also scripts. While we're talking about SD cards, one thing to note is every now and again we will see the odd dodgy SD card. It's just natural sort of manufacturing things. If you are sort of exhibiting some issues or maybe failed logging, it would be worth maybe swapping it out, checking it is connected properly, checking the contacts and terminals. It's just something there that very, very occasionally can go wrong. So to the front, and we have our nice range of connections on here. GPS1, I2C, we've got some CAN connections. What's important to note here, these are a JST GH connector, so quite a small connector. It has a lock on it, so here's an example of a CAN cable. Now most of your devices will come with the correct connector on, but one of the questions we get asked a lot is, someone will buy a device that doesn't have the right connector on, and how do we change that? So here's an example where this LiDAR here doesn't have the right connector, this will be connected to I2C. So for professional users, you may who do this every day, there is a particular crimping tool. So this beast here, but it is quite expensive, and it's not something suitable for hobbyists. But that's the sort of tool you would use if you're day-to-day crimping and producing drones. What I would recommend, say a hobbyist user does, when you've got your flight controller, whichever brand, you will probably have received a cable pack inside the box. So the easiest method to do this would be to resolder the connectors, so making the cut on the device and correctly soldering up the right wire order, and to use one of the cables that you have spare within your flight controller kit that you've purchased. It is very hard to find a sort of non-official crimping tool to do these very small connectors, and what I've seen in the past is people that try often have a failed crimp and then lead to a disconnection and ultimately the device not working. So for people that don't have the correct crimping equipment, I would recommend that you solder one of the included cables onto the device in order to have the correct connector. So let's have a look at what plugs into some of these ports. GPS 1 and GPS 2. Now for a long time we've had these two GPS ports, and these are serial GPS connections. They are a serial port that can be used for anything. It could be used also for telemetry. So visible here we actually have 4 serial ports: GPS 1, 2 and telemetry 1 and 2. Now GPS 1 is an 8-pin port on here. So I had to hunt around to actually find one with 8 pins on, because we've sort of switched over to CAN now. So this is a old here with the 8-pin connector, and the reason for these extra pins in this case is for the safety switch. Now on some flight controllers you might find a GPS 1 socket with 10 pins, and that's because they also have in a built-in buzzer. That's what those extra pins are for. So the difference between GPS 1 and GPS 2 on this flight controller is GPS 1 has 8 pins and it would also drive the safety switch, whereas GPS 2 is just a straight serial connection. If we plug in a GPS into 1 and into GPS 2, by default that would be their order. What we're seeing now is a lot of GPSs, such as here 3 here, we've moved over to CAN, or dual CAN in this case. Also the likes of this Holybro F9P, this is the new CAN based version. And what we could use here is this would connect into one of the 2 CAN ports. You can mix and match your GPSs. You could have GPS 1 as a serial and another GPS as a CAN. You could have multiple serial or multiple CAN. So what CAN offers is, CAN is commonly found on in the automobile industry. It allows you to have multiple devices daisy chained onto one port. So GPS is one example. I'm just going to show you a couple of other examples. So this is a optical flow sensor. This would also be connected via CAN. Now we could plug them into CAN 1 and CAN 2, or what's included with most autopilots is a splitting device. So this is just a commonly connected row of 4-pin connectors. So this could allow us to plug in multiple CAN devices into one socket. One thing we should do, CAN's great. So one of the benefits to CAN over serial, other than connecting multiple devices, is the data cables can run great distances, but the power provided from the port is only a small amount, and also you have voltage drop over distance. So here's an example of a product if you are connecting multiple devices and potentially over longer distances. This is a splitter that also accepts a power input, and it will provide a high current output to all these devices to make sure they have sufficient power for longer power runs and for power hungry devices. So this is quite handy. Nice aluminium case, can be bolted down, and it takes a wide voltage input from 2 to 12S. We picked this device up earlier on. This was a LiDAR that doesn't have the correct connector on at the moment, but this particular model is a Benawake TF Mini Plus, and this one is the I2C version. So that could be connected into the I2C port. I2C is different to CAN. You can't plug in multiple devices into this one port, but it's a nice way of connecting these small LiDARs. We do also have some LiDARs that will run off serial. So here's an example of a Lightwear LiDAR that's commonly run over serial. This one does also have the ability to run it off I2C as well, so you just define that in the settings. So the other ports on here are telemetry 1 and telemetry 2. So the sort of things you might connect into there, and they are a serial port, so you could connect to GPS, but the most common use of telemetry 1, for example, is to power a telemetry radio. So here's an example of a Holybro 433 radio, and this, with the included cable, would connect straight into telemetry 1. Here's another example of a telemetry radio. This is the RF Designs 900X. This one's for the US market. What you should watch out with, say, a more powerful radio is there is only a certain amount of power provided from the telemetry port, and it is best practice and recommended with any RFD radio to power this separately. Even on the lowest power settings, you should still power it separately. Don't rely on the telemetry port to provide enough power. So here's a cable that we include with the RF Designs, and what it does is it has a breakout for the telemetry connection, and what you'll see here is the actual power cable is missing. So the first cable is missing, and what we also have is a red and black wire here to provide dedicated power to that radio, so that misses out any power being taken from the telemetry port. You should also bear in mind, when you have lots of devices connected to any flight controller, which ones maybe want external power. So there is certain LiDAR modules, like this one is, I know this is a long range, quite powerful one. I would look to power this separately. This little one here, which is a sort of short range, low power, I would be very comfortable powering this directly from the I2C socket, or the other versions where it's a serial connection. As we just mentioned about having many devices connected, when you do your initial firmware flash, you will likely just have the USB connected and no peripherals. Later on, when you've fitted your cube to your vehicle and it's fully connected up to GPSs and LiDARs and telemetry radios, what you might find is if you plug in the USB in order to perform, say, an update, it won't have enough power from the USB to start up. So you either must remove some of these connections, or you would also want to power up from the external power 1 socket in order to allow the flight controller to boot up. So that's just something you should be cautious of when you have lots of devices connected. To anybody sort of building or starting a new project, or maybe you're new to assembling a drone, I would always recommend you start very simple. So your end goal might be to have multiple GPSs and LiDARs everywhere and many other peripherals connected. Keep it as simple as possible and sort of gradually add those extra items. So add your second GPS and then add your downward facing LiDAR next, once you've done your testing and flight tests, and sort of progress up to the higher level. Don't just connect everything in one go and go for your maiden flight when you've never built a drone before. That'll be heading for disaster. One other thing to comment on, so let's have a little look at a connection here, for example, to a small multi-rotor. So here we have again a power distribution board. This could be a typical speed controller, so a 20 amp ESC here. We can connect these to sockets 1, 2, 3 and 4, for example, on a quadcopter. So quite common, people ask, okay, this is good for the small multi-rotor. What happens if I am building a gigantic quadcopter or coax that runs 12S and is very power hungry, consumes hundreds of amps? So there might not necessarily be a product like this in your size. This is an example of a power distribution board that was taken from a sort of crop sprayer sized drone, and all this is simply a dumb board, if you like. There is no built-in current or voltage sensing. It is just a method for taking your feed from your batteries, so in this case it would double 2 6S's to 12S, and providing distribution from here. If you're using an amount of current that is, say, outside of available current sensing, what you could do is just monitor the voltage. So you could connect one end of a voltage sensor that does the correct range, like 12S or 14S, and provide your autopilot with voltage only reading. Now, the reason why you want a voltage reading or ideally a voltage and current, is this is something that's used to set your fail safes. So everybody wants, when their drone is going low, to be able to trigger a fail safe in order to land safely. You don't want to be in flight with a low battery. So if you are building the larger drones, you might need to put a little bit more detail into, is there an available current and voltage sensor what I'm trying to do? Could I maybe just measure voltage? And for some more elaborate systems, for example on some VTOLs, you may have different batteries for lift and for forward thrust, in which case you might actually end up with two current sensors, which you would connect to 1 and 2, and you could then tell it which one is for the forward motor and which one is for the lift motor. One other little thing to cover related to this picture, so we have there an example of the adhere link. So I'll just show you the basic connections to the cube using a adhere link. So here we have the air unit. I don't have the antennas connected, but what we have here is a port labeled S-bus and one labeled UART, which is the serial. And what the air unit requires is a power connection and these two other wires. So in this case, we have two cables labeled S-bus. That's because it will actually output two lots of 16 channels. So one could be for the flight controller, one could be for a gimbal. So this would simply go into RC in. And this cable here would go into a serial port, telemetry port. Let's use telemetry 1. And that is how we would wire up a adhere link in this case and providing a power. So what the adhere link does here, it has S-bus output going into the RC in. That gives you your stick control. And this telemetry connection, the serial connection here, this gives it all the information to run the on-screen apps like Q ground control. So that's giving it telemetry information, giving you all your stats, your height, your flight time, and then the final part of the adhere link is that we have video, so HDMI in up to 2 HDMI inputs. And that concludes our sort of overview and whistle-stop tour of connecting up an autopilot such as a Cube Orange Plus here.
Thank you for watching the video. If you watch my videos and find them useful, then please take a moment to hit the like and subscribe button. It helps the channel a lot. If you really like what I'm doing here, you can become a Patreon and support the time I spend helping others and get access to lots of exclusive benefits. Link is in the video description. Remember that all the videos on the channel are organized into playlists, so you can easily use those playlists to find all the videos on a subject that you are interested in. Add Painless 360 to your searches on Google and YouTube, and it'll help you find my content for any particular topic. Thanks again for watching, and as always, happy flying.